Hi, this is going to be another update on my bots of the SOC project. Unlike some of my last videos, which was just me commenting over some of the code running, this time I'm going to take some time to explain exactly what it is and how it works, so hopefully it will be a bit more understandable to a less technical audience. And it has been a while since my last update, but this is a side project that I'm doing alongside my work, social life and keeping fit as well, so bear with me on that. In this video I'll address a few key questions, starting with what actually is it? How does it work? How did it perform? Is there anything we can learn from this project? And then finally, how can it be improved? So what is Bots of the SOC? If you work in cybersecurity, you've likely heard of Splunk's annual Boss of the SOC competition. For those who haven't, this is a competition held annually both in person and online. Teams and individuals are given access to realistic SOC data and then compete to solve various challenges representative of what you would find in a security operations center. I had been experimenting with large language models and modern automation frameworks to see if I could automate some low-level security operations tasks. Then I realised that Splunk publish all of their Boss of the SOC datasets, and the answers are easily available online. I could use this to build an evaluation to empirically test the effectiveness of this approach. Hence, Bots of the SOC is an attempt to automate the solving of the Boss of the SOC challenge. So how does it work then? I'll start quite simple and then go into some more technical detail later on. So starting really simple, if you've ever used ChatGPT, you'll be aware that it remembers the context of what you're talking about within a conversation, but not between conversations. In the example on screen, we're asking about what the moon's made of and then how long it takes to get there. Notice we didn't specify getting to the moon. It knows that the there in this context refers to moon. Our user input in this context is known as the prompt, which we control. As well as the user prompt, there's also something called the system message, which is basically a primer that tells the agent what it is and how to respond to the context of the conversation. The process of prompt engineering is where we can refine both the user prompt and the system message in order to get the best possible results from our LLM. If you've used ChatGPT for the website, it handles the conversation history for you. However, if you use the API, this is not the case. For each API call, you get a single response back. It's up to you on your application side to track the conversation's history. So the conversation you see on the screen now will be stored in JSON format and look like this. You can see the system message and the user messages. You pass this whole block to the API and it returns a single response. With that out of the way, I want to briefly talk about benchmarks. There are lots of benchmarks for gauging the performance of LLMs. The most popularly known of which is called the MMLU, and you can see here on the leaderboard hosted on Hugging Face how different models perform against it. All common benchmarks operate in a similar way. The LLM is given a single question and responds with a single answer. This answer is then judged whether it is correct or incorrect, and the LLM is scored accordingly. There is a technique called end-shot learning, where the model is given multiple questions and answers, and it has been proven to improve the performance of models against most benchmarks. However, the previous questions are still presented in the same user prompt. The example questions are appended before the final question in what can be known as a pre-prompt. Another technique that's used to improve the performance of common models against standard benchmarks is something called chain of thought reasoning. Here, the model is asked to explain its reasoning step by step before going firm on an answer. All common benchmarks assess a model's ability to recall data it intrinsically knows, or to make reasoned assessments based on data it intrinsically knows. This is what these techniques improve. However, this is not representative of how we'd want to use a model to automate more complex tasks. So we give the model a question where the answer could not possibly be stored in its memory. It has to figure it out from experiencing the real world. Here, instead of asking the model what the moon is made of, something which would have been in its training data, we ask it what the object in our hand is made of, something it could not possibly have known during training. To help it, we give it some sensors to help it explore the real world and explain to them how to use these tools. The output from these tools is then fed back into the model as the user input. The model can then apply its reasoning and knowledge of the world to analyse that input and either request more data or return the final answer back to the user. Although this approach uses both multiple questions and logical reasoning to derive the answer, it is fundamentally different from the two prompt engineering approaches described earlier. To build my SOC bots, I've used Microsoft's AutoGen framework, which is a Python library specifically designed for using LLMs to work with tools in the real world. The most simple setup for an autonomous agent is a user, a single large language model bot, and something known as a user proxy. The user proxy doesn't require any intelligence itself. It can just be a tool. As long as the large language model knows how to use it, it can give the instructions to the user proxy to execute code, functionality, or whatever. The user has provided the initial system message, which explains how to use the tool and how to respond once the bot believes it's got the final answer. The bot then sends all messages to the user proxy, which returns all outputs back to the bot unless the final conditions are met, and then the answer is returned back to the user. It's possible to have more complicated architectures, such as a group chat with multiple bots and one or more user proxies. In this case, each of the bots can be given a different persona or personality, for instance, a project manager, an analyst, and so on. Another option, which in theory sounds good for more complex tasks, is to have hierarchical agents. In this scenario, the bot calls a user proxy, which rather than executing code, or Splunk queries in our instance, spawns more agent worker bots with user proxies. The master bot can break down the problem into smaller chunks and assign each chunk to a child bot to work on and then report back its findings. Because all large language models have a limited context window, which is a bit like their attention span, this should in theory prevent the master bot from getting bogged down in all the detail and leave its full context window for solving the higher level problem at hand. But some of you might be asking, wait, how does a group chat work? We can control system messages and we can control user prompts. So how does that work for a group? Well, each agent only has its system message and a list of user and agent messages as we saw earlier. These will get fed into a group chat, which is effectively just a history of the conversation up to this point. There's then another bot called the chat manager. The chat manager is given its own system prompt, which is basically, who should I ask next given the conversation history? It has access to a list of all the available bots it could ask, and then chooses one to direct the message to. The chat manager doesn't actually get involved in the conversation itself. It's just there to facilitate the exchange between the different bots. This does mean that both the chat manager and the receiving bot need to read the entire conversation string up to that point, which doubles your token usage. So let's bring it back to the SOC bot. How does it work? Well, effectively, a user provides an input. We then have a bot and a user proxy, which in this case, the tool it's provided with is the ability to query the Splunk API. This seems simple, but the Splunk API can return anything from a single line to gigabytes of text in one single go. When we use the Splunk web interface to search, the GUI gives us lots of clues as to what data is happening. We don't just purely rely on reading the lines. It tells us how many values there are, what the different values are for each field, and gives us a timeline, giving us a rough idea of how the data arrived in Splunk. I don't get this rich data from the API, therefore I have to build a wrapper function to handle the API's output for something more appropriate for the input for the model. I found the design of this function to be one of the most crucial elements for getting this to work. The pseudocode on the screen explains at a high level how the Splunk query function operates. First, the input from the model is checked to check it is correctly formed SPL and it will operate in Splunk. A common fault here was the model omitting the leading search command on a lot of searches. This is implied in the web GUI and therefore doesn't need to be entered, but needs to be explicit in the API. The function then tries executing the query and returns results. If this doesn't work, it goes into a debug function. The debug function here has been annotated with a little robot emoji. This means that it's a hybrid AI and classical function. This uses a mix of traditional coding and actually calls GPT-4 internally to help assist with the debug. This GPT-4 call is not part of the original chat. It's only there to help debug the function. If it can resolve it, it will execute the corrected function and then return the results with some text annotating how it has corrected the function. The results are then checked to see if they're too long. I wouldn't want to, for instance, return 50,000 rows of text to a large language model because it would just fill the context window. If the rows are too long, it truncates it to the maximum row count. If the single entry is still too long, it then calls another hybrid function which summarizes the data and then returns a summarized output using GPT-4. The advantage this has over returning the long response directly to the conversation is the context window for this chat can be taken up entirely by the summarization. It does not need to concern itself with the background or back history to the conversation before that point. Thus, only the really useful information is returned back to the main chat, focusing the context window on solving the actual problem at hand. To build a useful SOC assistant, I could leave it at that. However, I said I wanted to be able to solve the boss of the SOC question set without any human interaction. So I expanded my code to iterate over the boss of the SOC question set and use some of the prompt engineering techniques discussed earlier. The questions have now replaced the initial user input. To automate the full evaluation, I iterated over each question in the dataset and gave that to the bots. The bots then returned its answer to a marker bot which had the answer. It could then compare against the answer and decide whether it was correct or not. This is a bit more comparable to how a human would mark it, so it's not necessarily exact string matching, but if it's close enough that a human would have given it, the marker bot will give it. The marker bot then writes its output to a CSV. I had intended to run the entire Boss of the SOC version 2 for each evaluation with 3 different random seeds, so it would attempt each question 3 times. This would give me a really good understanding of whether it just got lucky on one answer or it can actually consistently answer the questions. Unfortunately, this ended up being too expensive, so I did cheap out a bit on this and didn't do the testing as rigorously as I would have liked to have done. So how did it perform? Well, not particularly well. So out of 45 total questions it answered, it got 11 correct and 34 incorrect. Different questions are worth different points. Out of a total of 520 available, it scored 115 or 22%. As you'd expect, it got more of the lower point questions correct than the higher point ones. I tried all 3 different architectures, the group chat, the single agent, and the hierarchical, but ultimately the simple single agent proved to be the most effective. I tried lots of tuning and tweaking with the system messages, the prompts, and the functions, but ultimately it just wasn't getting really much above the 24% I think I reached a bit of a plateau there where with the GPT-4 base model, that's about as good as I'm going to get it on this sort of task. Now, I discussed earlier about the different benchmarks. There isn't a known or common benchmark for these multi-step reasoning tasks. This is an area of emerging research, but there is yet no standard. So although GPT-4 performs very well on stuff like MMLU, we don't really yet know how it compares to other models for these multi-step reasoning tasks. And as far as I'm aware of, no one is yet optimizing models for agents for multi-step automations. So what can we learn from all this? One theory I have is that autonomous agents are very sensitive to creeping cumulative error in their base models. Say a model has a 90% accuracy on a basic one-in, one-out evaluation, but it has to do multiple steps to get to the answer of a more complex evaluation, like the boss of the SOC challenge. If each individual step only has a 90% accuracy, by 20 steps the accuracy could be down as low as 11%. Numerous times I saw the bot going down a rabbit hole with completely the wrong answer. On a few occasions it latched onto the user agent field where it's trying to look for the username. It would occasionally get part of the answer correct and then forget itself later in the conversation. I even tried adding a sense checker bot to the group chat just to try and get it to call out its mistakes. However, I think partly due to the reinforcement learning that OpenAI has applied to these models, it's not very confident at calling out mistakes. It's more tuned to be helpful than it is to be confident. So what next? How could it be improved? There are proven techniques to bootstrap the performance of large language models at inference time. However, a lot of these would be impractical or not financially viable to do purely through the API. In this paper that came out of OpenAI last year, they were able to considerably improve on the performance of their models using step-by-step verification and majority voting. But this would drastically drive up costs. I think it would probably be possible to fine-tune a model to optimize it for SEAM commands. Splunk publish a lot of suggested detections on their website and GitHub that comes with both the detection logic in SPL and a plain text description of what the search does. This would be very high-quality training data and probably would be suitable for training a model. There's also a lot of open source Sigma rules available online that could also be used to build a fine-tuning dataset. I think it would be possible to fine-tune a model on this and maybe use it as part of a group chat along with GPT-4 for more general reasoning. The other option is just to wait for a more capable model, with GPT-5 rumoured to be dropping later this year. If this sees the same level of performance as GPT-4 did over GPT 3.5, I think it will be very easy to come back to this project and score incredibly high results on these boss of the SOC challenges.